But that's it.
Oh, yeah. Calibrating your stack.
Welcome everyone. We just had a fantastic presentation at the ITC colloquium by Wren Suess, and she will discuss some more about the Webb telescope data. But apparently there is too much data. She doesn't have time to publish it, and moreover, she wants help from theorists in what to make of it, right? Especially the cluster galaxies that you have such fantastic data on. So we would like to hear more of how we can help. After obviously she is from Stanford, and the title will be a JWST view of massive quiescent galaxies at cosmic noon. And then we'll hear from Jasmine Gill, our own. Where is Jasmine?
Right here.
Oh, over there. To tell us about using the moon to search for the light nights in the dark, by which she probably means gravitational wave sources, right?
Yeah.
Okay. And then we'll hear from Ulrich Steinwandel from Flatiron. Where is? Oh, over there. Who will tell us about do magnetic fields regulate star formation in the dwarf galaxy ISM, interstellar medium, right? And finally, we'll hear from Kamlesh Rajpuri from the CFA, from here, over there, who will tell us about new insights into the largest particle accelerators of our universe. And by that, you don't mean the Large Hadron Collider, something much, much bigger and better. What is the maximum energy that we're thinking about? The maximum energy, 10 to the 20 electron volts, also 10 to 21. Yeah, just expensive. Yeah, it comes for free, but I guess the problem is that it's not near us. Thank you. So we'll start with Wren. Go ahead.
Awesome. Thank you so much for that introduction. Yeah, so if you missed my talk this morning, I was mostly talking about this new survey that we're doing in Able 2744. We're getting all of the medium, or we already got all of the medium band filters on NearCam. So it's a really lovely survey. All the data is public. If you're interested in using it, please come talk to me. But for this talk, I wanted to highlight some other work, also with JWST, looking at massive quiescent galaxies at cosmic noon. And so I mostly want to talk about the size evolution of quiescent galaxies. So I want to give you a pre-JWST sort of update on why this is an interesting topic. So this was actually, I think, one of the most surprising things when we first got observations from WFC3 on Hubble, is that quiescent galaxies, so galaxies that are red and dead, they're no longer actively forming new stars, seem to grow extraordinarily rapidly. So this is the size at fixed mass as a function of redshift or look-back time of these quiescent galaxies, and you can see they're almost like quadrupling in size in not very long. And the question is why they are growing, because they're not forming any new stars, so they can't change their sizes through star formation. And so just this sort of size growth is telling you something interesting about how these things are continuing to evolve after they die. And so there's a lot of hubbub for many, many years in the literature about why these things change their sizes. The first thought is that after galaxies stop forming stars, they continue to grow by accreting these little minor mergers, these little galaxies that effectively poof up their outskirts. However, you can go measure the number of close companions around these things and actually calculate the minor merger rate. And it can explain the size growth at sort of low redshift, like redshift 0.5. But there's this big gap between this model from Drew Newman here shown in red and this data shown in gray. So basically, there's a factor of 2 extra size evolution in these quiescent galaxies that you couldn't explain through star formation, through minor merger growth alone. And so the question is like, is this a selection effect? Maybe it's something weird about how you're building your population. Maybe the galaxies that are dying at later times happen to be larger, and so they're changing the median. There was sort of this debate as to what was happening. But galaxies look different at different wavelengths. This is an example of a galaxy seen by HST. And these sizes are calculated at rest frame 5,000 angstroms, which is like here. And so what you're really tracing is not necessarily the actual stellar mass distribution of the galaxy. And to do that, you need to go to much longer wavelengths. And so we tried to do this pre-JWST through actual spatially resolved stellar population modeling. And we suggested that maybe if you look at the actual mass profiles of galaxies, this size evolution is slower, and maybe it matches up with the minor merger model. But all of this is very model dependent, and it depends on how exactly you're making these measurements, because you can't directly look at the rest frame infrared at cosmic noon. And so we wanted to actually do this with JWST once you could start actually looking at that rest frame infrared. And so we started looking at some really well-studied massive quiescent galaxies in JWST. This was work with the JADES team. Daniel and Ben are on it, many other excellent collaborators. And one of the first things we noticed before we even started looking at the longer wavelength data, we started looking at the JW data at 1.5 microns versus the Hubble data at 1.6 microns. So these should look the same. And the main galaxy basically does. But hopefully you can see in these JW images, something pops up, which is there are all these itty-bitty little sources around all of these galaxies that we couldn't see before at all in the Hubble imaging. And so if you subtract off the main galaxy, everything that I've circled here in green, we did photometry on these galaxies, subtracted images, and fit for the redshifts. Everything that's in green is at the same redshift as the thing in the middle. And so what we think we're seeing here is actually satellite galaxies of these massive quiescent galaxies that were completely invisible before with Hubble. And so if you put this in terms of the stellar mass ratio, so how faint are these companions compared to their host as a function of how far away they are, that part of the diagram up there is what you could see with HST. So you could see companions that were about 10 times fainter than their hosts. And that was what that model curve for minor merger growth that I showed you was built off of, was these really massive companions. And in like Milky Way terms, this is basically like saying that you can see the LMC, but you can't see any other satellites of the Milky Way for these galaxies. And then when you look at them with JW, you're revealing this giant population that's at lower masses that we can finally start to resolve due to this combination of both the amazing depth of the imaging and then the about 3 times better resolution. And so we're seeing these companions that are up to like 10,000 times fainter than their host galaxy. And so the question is, what effect do these things have on their hosts and on the evolution of these quiescent galaxies? There's something like 30% of the total companion mass, so it's possible that they don't necessarily change the size growth picture too much, though we, I think, need to make some more detailed measurements in a much more careful way than we did for this paper. But they are a very different color. So here I'm showing you the difference in U minus V versus V minus J color between the central galaxies and these companions, where the big squares are the things that we could see before with Hubble, and the little purple dots are the things that are new with JWST. And so basically the things that we could see before were similar color or even redder than these red and dead quiescent hosts, whereas all of these little new things are all significantly bluer than their host. And so as those things merge in, they're probably going to make the outskirts of these quiescent galaxies significantly bluer, probably because they're younger or lower metallicity. And they're actually probably going to drive evolution in the color gradients of these quiescent galaxies, that as we observe them to lower and lower redshifts, we can start to see this evolving color gradient. So I think in 10 minutes, I don't really have time to connect it back to exactly what we think this means for size growth. We've looked at this as well. So this was a paper led by Zhuyan Ji, who actually went through and used this same sample to calculate how the sizes of these quiescent galaxies are changing. And basically the picture is that they are evolving slightly slower, and the sizes are slightly smaller at these longer wavelengths. And so basically, in terms of understanding this size growth of quiescent galaxies and how these things are continuing to change after they die, basically with this new data, we need to rethink both actually how much the sizes are changing with redshift and how many minor mergers there are. And so basically both parts of this picture, we had incomplete data because we weren't able to go to these really red wavelengths at high resolution. But the other thing that's really exciting about this is basically we can now study the demographics of satellite galaxies at redshift greater than 1, which is basically a regime that we have not ever been able to probe before. And so this is my attempt to tell you that this new telescope that we have is not just good for high redshift things in terms of galaxies, it's also very amazing for low mass galaxies in the more local universe, even if it's not getting quite as much hype on the archive. And so the exciting thing is that in the simulations, the actual population of satellite galaxies that you get is really sensitive to a lot of things that we care about a lot. So the number of satellites depends on what you think dark matter is made of. It also depends on a lot of details about how you're tracking your subhalos as they merge into these main halos. And then your method for implementing the galaxy halo connection and actually painting baryons onto these dark matter subhalos. And so we have a Cycle 3 archival program that I co-PI'd with Riso Wexler at Stanford. A lot of the heavy lifting is being done by Jenny Wan, who's a really amazing grad student at Stanford, where we're actually going to go use all of the public data now that we have from JWST to measure these satellite luminosity and mass functions at cosmic noon for both star-forming and quiescent galaxies. We're going to measure this galactic conformity thing, which is how the properties of the satellites compare with the properties of their host. And then also actually we hope we're trying a very proper comparison with the theory and get this nice new redshift lever arm on how this satellite population evolves with cosmic time. So I hope I convinced you that the size evolution of quiescent galaxies is interesting. We can use this to constrain their formation and evolution, but also we need to rethink our picture of this size evolution now that we have access to all of this new data. And in particular, JWST is revealing many of these faint companion galaxies that we haven't seen before around even these extremely well-studied systems in some of the deep fields. And then we can study the satellite population in detail now, and we're hoping to do that in the next coming years. So, thank you.
From a theoretical point of view, 10% is an interesting number because satellites above 10% of the host sink to the center by dynamical friction. Many simulations show that. And those below 10% stay in the halo. So now we're able to see the progenitors of the satellites we see today because they would never reach and merge with the central part of the galaxy. And that would be an interesting mapping to make. Mm-hmm. The larger than 10% would have been lost by now in the course of galaxies.
Yeah, that's a great point. The other funny thing about 10% when you're thinking about it is we were looking at only quiescent hosts, and something that's 10% of the mass of the host is probably, I would assume, going to reignite star formation as it falls in. And so you're no longer going to have it in your quiescent sample. And so we're actually seeing really this dominant population now as well.
Exactly. Yeah. Thank you.
Yeah.
Comments? Go ahead.
Can you say if the satellites themselves are quiescent or stop forming? Because there was like this discrepancy with SIGA survey. Most of the satellites are stop forming while nuclear, so it's higher chance of this.
It was difficult
Yeah.
to hear the question.
Yes, so the question is, can we say whether or not these satellites are star-forming or quiescent? So I think we need to actually do better measurements. This was sort of a first order thing that we did. They are, if you look at the star formation rates that we got out of our modeling, they are relatively star-forming. They're, I think, specific star formation rates of like -8 on average or something like that, so not highly star-forming. They are all bluer than the host. But I think to make definitive statements about conformity, we need to do a much better job with understanding our completeness and contamination.
Any other questions, comments? Please go ahead.
If you look at the early type galaxies in
Yeah.
the local universe and you study, do some archaeology, stellar archaeology of the early type galaxies, where you see some discontinuity, will have some hint at which regions happen and redshift may be higher.
Oh gosh.
6 or 4 to see this kind of minor merger residences. Is it
Yeah.
possible?
I'm not sure.
Yeah.
That's a great question. I don't know the answer. Yeah.
And just a point of reference, Wren is starting a junior faculty position at Colorado, right?
Yes. Yeah.
Pretty,
Thank you.
pretty soon, is it?
Yeah, in the fall. I'm very excited. I feel very lucky.
Congratulations.
Thank you.
Good luck.
Thanks.
Let's thank Wren again.
Okay, let's change gears for a second and go back into gravitational wave land.
Just make sure it's on.
Yeah, can you guys hear me okay?
Yeah.
And amongst other features, this is a great story. The short movies, we've actually absorbed sonic so there's cool gas coming out.
Okay, all right. So thanks so much for having me. I'm a final year PhD. Most of you know me as Jasmine. And I specifically work on understanding gravitational wave emission from core collapse supernovae, which is what I call my light nights in the dark. So before I get into the details, I just want to recap everyone saying, you know, the birth of gravitational wave astronomy started in 2015, right, with the direct observation of 1509-14. But the first inaugural electromagnetic detection happened right here in-house with 1708-17. But the next watershed detection still remains yet to be seen. And in my eyes, that's the detection of core collapse supernovae, gravitational waves from core collapse supernovae, more specifically. So how do we start to understand these light nights better? So quick overview, what happens if you put LIGO on the moon, you know? What sensitivity in the gravitational wave frequency spectrum do we access? More particularly, are we able to access more low frequency gravitational wave emission from these more vanilla core collapse supernovae candidates? And if so, what's the detection prospects look like for these sources? So really quick, before I get into core collapse, let's talk about lunar LIGO, or how I would like to say LILA for now, which we had a fantastic talk by Karagnani a few weeks ago on the laser interferometer lunar antenna, what we call LILA. And this actually originally started from a concept that was founded right here by Avi and Karan called the Gravitational Wave Observatory for Cosmology, otherwise known as GLOC. But again, as I was saying, you know, there's this spectrum, this gravitational wave frequency spectrum, that terrestrial observatories such as LIGO, Virgo, can only access about 10 hertz to about 1,000 to 2 kilohertz at most. PTA has come online. We have space interferometers, LISA, that can access, you know, a lower frequency band, but there exists this gap in the sub-hertz frequencies, right? So think 0.1 hertz to 10 hertz. Can we get there? How can we get there? Well, if we put a LIGO on the moon, So let's say we have, instead of 2 L shapes, we have a triangle that we have 3 bases, and they're all separated by, let's say, 40 kilometers, right? So let's take Einstein telescope and put it on the moon. Are we able to access these frequencies? And if so, what kind of science is in there, right? And so this is a really nice graphic. Again, I'd just like to point folks to this link, which gives you a lot more information about the Lila collaboration itself. But within this frequency spectrum, you can access IMBH science, type 1a white dwarf mergers. But you can also access gravitational wave emission from core collapse supernovae, because it just doesn't stop within this frequency range. Theoretically, we have emission all the way 10 to the minus 5. But, let's not, expect that out of our experimentalist friends. So, again, moving forward, for my folks in the room, right, what are core collapse supernovae? They're essentially gravity bombs. So any star, theoretically, that's more massive than 8 solar masses is going to go kaboom, right? So I think of core collapse supernovae as really sophisticated, onions with a lot of shells. But as the silicon shell, fusion is occurring in the silicon shell, the iron core starts to get more and more massive until it starts to exceed the Chandrasekhar mass, right? Which is ideally the maximum mass a crust can support. And that's where we start seeing these gravitational wave instabilities, where the iron core is supported by the degenerate electron pressure, but then the gravitational force starts to overpower this pressure force, and so we start to see a collapsing of the iron core. Now, all the nucleons are becoming nuclear pasta, right? And then we reach these super nuclear densities, and we're really compressed. And then we have essentially a stiffening of the equation of state and a rebound of the core. And we have this shock wave that's essentially mostly what we think is powered by neutrinos. Now that shock, as it travels through the star, right, and it's ripping through its layers, starts to stall because we're losing energy from the neutrinos. And the shock goes from being dynamical to this standing accretion shock instability. Okay, so it just means it's also moving slower. But eventually, so we have a stalling of the shock gets revived again. There's a little bit of mystery that happens here simulation-wise that we're still resolving. But essentially for our astronomer colleagues, we eventually see shock breakout, where the shock breaks out of the stellar surface itself, right? Okay, cool. So we know that core collapse supernovae are multi-messenger machines. We have photons, we have neutrinos, we also have gravitational waves. The time scales, though, are different, right? Because post-bounce, as soon as the iron core collapses, we have the generation of gravitational waves, but it only lasts for a few seconds. Whereas our photon emission, we can see them days, weeks, after explosion, post-shock breakout, right? So let's talk about gravitational waves. All right. I'm going to show you this plot. Don't get scared. So this is representative of an older simulation in 2 dimensions that's essentially showing for a 15 solar mass star, what would the potential gravitational wave amplitude look like? So the y-axis, just think of it as I've injected this signal at a specific distance, and we just multiply the strain. Now, one important thing to note is, wow, Jasmine, maybe you guys have seen recent 3D simulations, but these amplitudes are really large. Just keep in mind this is 2D, okay? So these amplitudes, as soon as we hit, our recent 3D simulation buddies, they drastically reduce from, like 100 centimeters to about 5. But the most important part that I want to highlight is up until this point, we've been seeing this really nice convergence of all our 3D simulation groups coming together and agreeing on a few of the effects that are seen through the gravitational wave strain that is primarily from the asymmetric, aspherical matter motions, right? So there's matter that's doing all this fun stuff as the star is blowing up, but then there's also neutrinos. And so this black line shows particularly just the amplitude from the matter motions, but then one thing I want you folks to notice is red line represents, okay, the star has exploded, but this other black line up here is actually the gravitational wave strain amplitude from neutrino emission, which you can start to see just starts increasing. And so that was like a really interesting thing that emerged early on but needed a lot more development, and I'll get back to that. Because Yeah. And so, okay, so I talked about this plot and I said, okay, once we go into 3D, I'm showing like a variety of progenitors. So this is for 15 solar mass. We go all the way from 9, 10, 12, 13, 19. And you can start to see, okay, you know, we have this prompt convection at early times. And really, if you're thinking of, Jasmine, this is a time series plot, but you're talking to me about, you know, frequency spectrums and gravitational waves. What frequency is this primarily associated in? This is about 100 hertz all the way to 2 kilohertz. But this signature right here from neutrino emission is very low frequency. So it's below 10 hertz, right? And so this is essentially the unique science opportunity that lunar detectors pose over traditional either our 3G, detectors such as Cosmic Explorer and Einstein Telescope, and then just for fun, I had put up the LIGO L103 strain. So what is this plot showing? Let's just take a typical representative, non-rotating 15 solar mass gravitational wave strain. Let's plot it, frequency against our noise amplitude. Let's plot our power spectral densities that we know from LIGO 03, Cosmic Explorer projected, Einstein projected, and we can start to see that, basically below 10 hertz, we start to struggle capturing the rest of that signal. However, if we add in the curve from Glock, and this is Glock, the optimal Glock curve, so there's two actually available on the website. There's Glock conservative and Glock optimal, but you can start to see that we are able to access a larger, lower frequency space. So then that brings me to my next point is that, okay, Glock is optimal, but realistically, where are we standing right now? So if you just take the sensitivity curve from the Lila website and put it on this plot, this is where we are, right? And so again, we have that unique edge that unfortunately, even when Einstein Telescope is up and running, Cosmic Explorer, et cetera, aren't able to access. We might still be able to go down to, if anything, 0.1 hertz, right? So this is just showing you if we were to deploy with Artemis initial Lila in, let's say, 2030 to 2035, this is what potentially the noise curve would look like. Okay, so really quickly, the takeaways. The moon presents a unique opportunity for gravitational waves from core collapse supernovae. There is the possibility of detecting more of a low mass population if we had lunar detectors versus our terrestrial detectors, because they are just more biased towards our 12 solar mass, 15 solar mass, 23. And the letter's coming out soon. And with that, I'll just take questions.
Jasmine, can you comment on what can we learn about the sources from the moon that otherwise we will not have access to from any other future observatory, like other sources that only that?
Yeah, so I'll just quickly touch on BNS, right? So binary neutron stars. Everyone's asking, we're in 04, 05's coming up, where are detections, right? And so a really interesting concept is that supernovae or not, lunar detectors present this early warning system, right? Just because we're able to access that frequency band before we hit the terrestrial interferometers, it allows us, for example, to observe merging binary neutron stars weeks to months beforehand, as compared to, for example, Einstein Telescope, which only gives us about, let's say, half an hour at most, ideally. So, there's just a lot, there's just a giant low-hanging fruit that is yet to be kind of, utilized from that end. But from our BNS folks, we would just capture a larger population there as well. But
of course, the fact that we can see it early means that there will be many more sources.
Yes, exactly, and it just helps in terms of, if ideally now that the LVK is becoming this like IGWN, right, we would anticipate that in 10 years our terrestrial localization is significantly better, right, in that sense too. But I'd like to just finish that off with, we have a white paper that's coming out very soon on IMBH, BNS, Type 1A, and core collapse science cases, so more soon.
It's certainly a very exciting future ahead.
I'm hoping.
We're used to dealing with light, but it's about time to change our
and to access this frequency spectrum that, the main, if anybody was to ask, okay, Jasmine, what are the experimental limitations, right? At higher frequencies, we have laser power and scattering and the mirror optics, but at lower frequencies, our main limitations are seismic, which lunar-wise, we're, let's say, a few orders of magnitude better there, right? And then our suspension optics, and our suspension system itself. So, we also have like this curve right now where it's like, okay, what if we put, Virgo tech directly on the moon? How would that look like? And then how would we slowly shift that to the left? But yeah, just hoping that with Lisa, we can just kind of ride along Lisa's coattails and say, okay, with Artemis kind of ramping up anyways and Artemis Base Camp becoming a serious concept, there is potential not only for like radio astronomy, but gravitational wave science as well.
So of course, the moon, aside from low seismic noise, there would be a vacuum for free.
Exactly,
You don't
exactly,
need to
right.
build the vacuum
Right. And just the main thing is now, okay, if we can, have like zones designated so that there's no nearby mining, and that, if we don't find a suitable crater, are we able to make use of the natural lunar geology instead of, crafting tunnels? And then there's also concepts of, this is technically, let's just put 3 landers on the moon and then just shoot lasers. But then what happens? There's lunar dust, but it's not that bad, but there is wind and lunar dust, so would it be helpful to put a beam covering over that? And so there is a paper by Jan Harms et al. From the GSSI group that really explores that concept back in 2022, 2023. So yeah,
Thank you.
Thanks very much.
Any comments, questions? Yes?
So one thing that worries me a little maybe, but you might be able to enlighten me more, is our predictions for these gravitational wave signals seem to be pretty heavily dependent on very expensive simulations of core collapse, right?
Yeah.
Can you comment on maybe how much those features have evolved as we've gone through different generations of things that cost millions of CPU hours, or what features might be somewhat independent of the details?
Yeah, so since I'm not a simulator, I won't speak on behalf of them, but I can give you a little bit of an idea of, for example, to run a simulation out for 6 seconds. So for example, I didn't show this plot, but I really encourage folks to check out this paper that was published last year, but they essentially run out their simulations all the way up to 6 seconds, okay, which is very impressive because most of our simulations are half a second, at most 2 seconds, right? And that in itself takes 9 months kind of thing, 9 to 12 months, right, of dedicated GPU and CPU hours, etc. But the nice thing is, if you have a 6 second duration, then your lower limit in regards to your frequency is about, hold on, 0.1 hertz, 0.1 to 1 hertz kind of a thing, right? These latest simulations that are about to come out from another group, we have like a moderate, I won't say too much because it's not published yet, but their lower frequency limit is 2 hertz in that sense, right? So one paper that I had co-authored with an undergrad back in 2022 was saying, okay, if we have these signals that actually don't have the memory component, can we attach a very simple cosine extension tapering function, right? Just to see how the signal would potentially look like. And that's why, this signal itself is original, but we do have tapered signals that will be in the letter. But then the other thing that we have to deal with is that there's just a wide range in the magnitude of the neutrino emission associated gravitational wave strains. So traditionally, again, we'd only expect a range of like 5 to 15 centimeters. But these that came out last year are going all the way to 800, 1100 centimeters, right? So in terms of, you transfer that into like detection distances, here at most, which I didn't show, I just showed a conservative 10 kiloparsec, so a galactic supernovae. But this, our lunar detectors can technically encompass also supernovae at 100 kiloparsecs. But with strains, with strains as strong as these, we might be able to go potentially megaparsecs, but again, I'm not making that statement right now for obvious reasons. So hope that answers your question a little bit. Cool.
Any other questions? If not, let's thank Jasmine again.
Can you hear me okay?
Not yet.
Not yet?
Oh, yes.
No?
Yeah.
It's better? Okay. Good. Thanks very much for having me, and thanks to Avi for actually reminding me of my real title. do magnetic fields suppress star formation in a dwarf galaxy ISM? I will talk about this, but I will also talk about some stuff on galactic outflows. So galactic outflows are important. Mostly, excuse me, sorry, because we care about galaxy formation, okay? So, and galaxy formation itself is kind of a solved problem. My advisor solved it in 2010, Ben Moster, write it down. He did it again in 2013, again in 2018, and with machine learning again in 2019. But it doesn't really matter, okay? It's a solved problem when you take the standard, you know, as Simon White would say, the standard solution to the galaxy formation is a semi-analytic model. Then it's solved because you have very limited model parameters, and you can do a lot of fine tuning, I would say. It's a little bit more complicated when you look actually at like what galaxies look like when you observe them, specifically when you look into multi-phase galactic outflows. This is M82, as many of you will know, right? So there we have to be a little bit more careful, and because we actually want to model the ISM, and we want to model the large-scale structure of this outflow, right? And specifically, I also want to understand what the magnetic field is doing to the ISM specifically. So what do? I actually simulate galaxies at very, very, very high resolution, like much higher resolution than almost anyone else. And what we do is we place this is one feedback event in one of my models. This is a 19 solar mass star that I put into a box at 4 solar mass resolution. Not the star is 19 solar mass resolution. And we have non-equilibrium cooling, non-equilibrium chemistry, and the photoionizing radiation of that star that's driving out the Strömgren sphere. And after you wait a very, very long time, in that case 8 megayears, and I'm already, this movie is really too long, I need to do something about this movie. But we're almost there at the core collapse supernova event, and that's the key aspect of these type of simulations. Because the nice thing about this simulation here is that actually the setup phase of that supernova blast wave is fully resolved in the model framework. So what can we do with this? So we can not only do the single supernova events, we can actually plug this whole thing into a full galaxy. This is what we did in a paper that I wrote with my collaborators last year. This is the largest simulation we ever did of one of these. It's an LMC type analog to study the multi-phase galactic outflow of that system. And that's, again, single stars at 4 solar mass resolution with a spatial resolution of 0.5 parsec gives you in total a few times 10 to the 8 gas particles in that system. And the whole simulation cost me like 10 million core hours or something like that. So it's a very, very complicated simulation to run. So then we do the complete opposite of what reasonable people would do. We go away from where we actually have the resolution in the midplane and look at the galactic outflows, which is a bit counterintuitive. And just to give you an idea of how we do this is we go to kiloparsec, 3 kiloparsec, 5 kiloparsec, and 10 kiloparsec, and slightly increase the slab size, just compute the flow rate for mass and energy. And what we ultimately try to do with this is build a model for the mass and energy outflow loadings that we can plug into large-scale cosmological galaxy formation simulations. But I'm not going to talk about that aspect today. So you can actually then plot this as a function of time, and what you will learn is that at low altitude, here the black lines at a kiloparsec, we get fairly high loadings at around 1, a few in mass, and around 0.1 in energy. And that's actually quite well in agreement with like what actually semi-analytic regulator models need to actually predict the realistic galaxy formation population, okay? So that's a very important aspect that came out of these simulations to relate to. What we can do on top of that is we can actually look at the multi-phase structure of this wind, and you can do this mass-weighted on the left or energy-weighted on the right. And what you will learn from this is that most of the mass is actually transported, this is in this figure, most of the mass is actually transported in a fountain flow. So most of the mass is actually reaccreted and contributes to star formation again. But most of the energy and the metals as well escape in the hot wind. And this is the first time that we actually did this for a global model. There's a lot of studies on this from my colleagues on like tall box type of simulations, and they are in very, very good agreement with one another, which is a very, very promising result. Okay, let's actually move on to the magnetic field part. So we can do these simulations. It took me quite a while to get this to work, but by now we can actually do these with the full MHD treatment. We needed to update some of our, this is a Lagrangian code, so we needed to update some of our divergence cleaning prescriptions to actually make this work. But now it works very nicely, and we finally get nice dwarf galaxies with a fully resolved ISM and a fully developed magnetic field structure in it. So what does that mean? Do we get anything reasonable out? So the first thing when you do an MHD simulation is typically check what your magnetic field is doing. And it was kind of disappointing when I first looked at it. Like the total gas is the black line here as a function of time. And that just didn't go anywhere. Like it turns out that actually it's quite hard to amplify the magnetic field in that particular system because the galactic outflow driven by the supernovae is so strong. So actually what this is doing in practice is actually reducing the magnetic Reynolds number of the whole system and limiting the dynamo. It changes a little bit. It's a little bit more promising if you look only at the dense gas. Then you actually get to the micro-Gauss level regime that is actually observed in molecular clouds. And to answer the question, do magnetic fields suppress star formation in the dwarf galaxy ISM? No. At least my simulations say that they don't, which is kind of frustrating because it's, yeah, well, I put a lot of work into that. And I was quite confident that it would do something, but it didn't. It's not quite true because it changes the burstiness somewhat. So if you look at this model, the dark blue line, this is the hydro run. And if you look at all the other runs, these are MHD variations I tried out. That didn't really do anything, but they changed the burstiness. But if you integrated star formation history, you still get almost the same total star formation. There's one run, though, which is doing something weird, and that's one that is not fully finished yet, where I tried a very, very high magnetic field, which I still have to analyze a little bit into more detail. But this is what I find. There is no suppression of star formation due to magnetic fields in dwarf galaxies, which is a little bit different than what we previously found in larger galaxies like the Milky Way, for example. So that's interesting in itself. And with that, I think I'm already out of time, and I leave you with my conclusions, and I'm very happy to take questions. Thank you very much.
So Ulrich, maybe you can answer a question that I was struggling with for decades. Mm-hmm. Does getting better data from observers make you happy? Or do you see a disagreement with your simulations?
It makes me always happy if there's more data. Well, of course it makes me more happy if there's more data, but it's always also tricky, right? Because that part, like, I worked a lot on are you referring to magnetic fields in general?
Yeah, for example, in the Milky Way, people claim for many decades that it suppresses stuff. I mean, do you get agreement with some of the basic observational claims?
Well, we do. I mean, there is some of that, right? I mean, we do get like adiabatic compression, like it's observed. That is there, right? I think the main point I wanted to make here is that it turned like if you do this in a different model, it's much easier to amplify that field. If you do this in like a effective equation of state model, like Springle-Hörnquist or something like that, you will have a much easier time amplifying that field because the outflow that you generate is much weaker. So that actually generated a problem for us, and I'm not the only person that has this problem. Like Romain Tessier and Ramsey is very different code. has the same issue. Like if we go to high resolution, we resolve the ISM, we get a strong supernova-driven outflow. It's very, very hard to actually get the field to any reasonable level. It's not the case at all if you do this in effective equation of state models. And it's kind of interesting that you get very good agreement from my old simulations even, like that I did with effective equation of state models. For Milky Way-like models, you get excellent agreement with a lot of magnetic field properties that are observed. And even more complicated things like dynamo scalings, which is another whole nightmare, right? Yeah, so long story short, I'm very happy to have more. It's just like in this regime where we put in all the physics, suddenly things change very dramatically. I think that's a way of phrasing it, maybe.
Okay, please go ahead.
Have you thought about looking into the lifetimes and star formation rates of like individual clouds?
Yeah, I did. I need someone to do it.
Cool.
Do you want to do it, guys?
I love starting projects and never finishing them. So.
No, it's on my long project list of things that someone needs to do. Maybe me. Yeah.
Any other questions? Yes.
Yeah, actually I had the same, or like more like now follow-up question. So simulation of individual gems show that magnetic fields can suppress star formation.
Yeah,
So for you it's like subgrid scale, right? So
right.
Something must happen in between. So
I mean, it's not subgrid scale for me, right?
I mean,
A GMC in my simulation has 10 to the 6 particles.
but those simulations are like parsec scale box, right? Resolve like. Right?
Fine. Okay. Yeah, I could have higher resolution. Yeah.
But something must happen in between, right? Or
There is
like it must
no, sure. I mean, that's where the burstiness actually comes from. I skipped over this. Like if you look at the MHD models, you see that the peaks are higher and lower, and that's actually small scale suppression, like on the cloud scale. But that doesn't necessarily translate into like a global regulation of star formation.
Right, so
like other people have claimed that that's actually the case. Like for instance, there's one Aripo simulation that's claiming this from like 2 years ago. And I tried to, like, the reason why this is not published is because I tried for a year to actually reproduce what they find and I couldn't, right? So I still don't know why this is happening in Aripo, and for me, I get that result, right? That's why this is not published yet.
Maybe a numerical.
It might be numerical, yeah. Very well, could very well be, yeah.
Okay, anything else? Let's thank Ulrich.